In today's video, we will be discussing dynamic mechanical analysis, or DMA, and how it can be used to determine glass transition temperature. Dynamic mechanical analysis is one of the popular techniques that can be used to study the viscoelastic behavior of polymers. DMA measures the mechanical properties of polymers as a function of time, temperature, or frequency. By the end of this video, you should understand the basics of how the DMA works, how to set up the DMA, and how to analyze data to determine the glass transition temperature. Let's get started. So what is dynamic mechanical analysis and how does it work? DMA works by subjecting a sample of material such as a polymer to an oscillating force while it is heated or cooled. The sample's response to the applied force is measured, which provides information about the material's mechanical properties with response to temperature. DMA is designed to apply a controlled stress or controlled strain to a polymer sample of known geometry and subject the sample to undergo sinusoidal deformation. A force motor is used to generate a sinusoidal wave, which is transmitted to the sample via a drive shaft. DMA measures the modulus as an in-phase component, the storage modulus, and an out-of-phase component, the loss modulus. The storage modulus, or E', is the measure of solid-like elastic behavior in a material. The loss modulus, or E', is the measure of liquid-like viscous behavior in the material. The ratio of E', divided by E' is the tan delta, also called the loss tangent, which is a measure of energy dissipation in the polymer. So how do we use DMA to determine the glass transition temperature of a polymeric sample? In general, the mechanical properties of polymers are determined by their molecular structures. At low temperatures below Tg, polymers are immobile and behave like stiff solids. At high temperatures above Tg, polymers have free volumes large enough to allow for segmental mobility. This leads to drastic changes in the polymer's storage and loss modulus. Therefore, the Tg can be determined using the step change of the storage modulus versus temperature, which also corresponds to the max peak of the loss modulus versus temperature. The first step towards running the DMA involves preparation of the sample. This involves cutting the polymer sample into a specific shape and size and attaching it to the DMA machine. The shape is usually rectangular with a length of around 10 to 20 millimeters, a width of around 5 to 10 millimeters, and a thickness of around 0.25 to 1.5 millimeters. This may change though depending on what mode you want to run the DMA in. Generally, a DMA will ask for a mode, test setting, clamp type, and dimensions of the sample. Common clamp types include tension, compression, dual cantilever bending, and three-point bending. The most suitable type should be selected based on sample shape, modulus, and measurement purpose. The most common modes include stress relaxation, frequency sweep, temperature sweep, and dynamic stress strain. Depending on what mode is chosen, extra parameters will need to be entered. For the determination of glass transition temperature, we will focus on using a temperature sweep with a tension clamp. After naming the run and saving the file, you can now press play to start running the sample. Let's now analyze some actual DMA data. Here's an example of a polystyrene sample that we tested on a temperature sweep with a tension clamp. The other test parameters were a 1 Hz frequency, an amplitude of 15 microns, a soak time of 5 minutes, and a temperature sweep at 3 degrees Celsius per minute from 35 degrees Celsius to 160 degrees Celsius. On the left axis is the storage modulus in megapascals, which is also represented by the green line. The right side of the graph has loss modulus, which is represented by a blue line. Loss modulus divided by storage modulus, or tan delta, is represented by a red line. As stated before, the glass transition temperature can be determined by the step change in the storage modulus, or the temperature at which the loss modulus is at a max peak height. In this example, we can see that the glass transition temperature, according to the storage modulus, is about 108.17 degrees Celsius. This value is very close to the glass transition temperature as determined by the loss modulus, which is around 108.80 degrees Celsius. This is very similar to the value of 100 degrees Celsius often reported in literature as the glass transition temperature for polystyrene. Now let's move to an example. Here's a graph of polyethylene terephthalate as run in the DMA. The left and right axes are blanked out and are for you to fill in. First, label the left and right axes of the graph. Next, identify the glass transition temperature using the step change for the storage modulus. Lastly, determine the glass transition temperature using the absolute maximum of the loss modulus. Pause this video if you need more time to answer these 3 questions. For question 1, the storage modulus should be on the left side of the graph, also represented by the green, and the loss modulus should be on the right side of the graph, represented by the blue. For question 2, we can see that the step change for the storage modulus is at 103.9 degrees Celsius. Thus, that is the glass transition temperature using storage modulus. For question 3, according to the loss modulus, if we look at the absolute maximum, the glass transition temperature of this PET sample would be 118.46 degrees Celsius. And that's pretty much it. That's how you can use DMA to determine the glass transition temperature of your polymer. As you can see, DMA is a powerful tool for understanding the mechanical properties of material, and it has many applications in the fields of material science, engineering, and polymer chemistry. Thanks for watching. Make sure to like, subscribe, and comment with future video ideas. Peace.